Good afternoon. Welcome to EE 380, the Stanford Electrical Engineering Computer Systems Colloquium, which meets every Wednesday. Our speaker today is Dick Seitz, who has a long and pretty illustrious history in the business. And he is talking about some of the work that he's reported in his Understanding Software Dynamics, his recent book, probably the most significant book of the year, I think. It's a great read. I'm not finished with it, but I'm making considerable progress every night. In any case, Dick's going to tell us about what it's like making the invisible web invisible, making the invisible visible. And this is the problem of how do you see what a complex computer system is really doing. And thank you for coming up and participating as a speaker. And just a little word of advertisement. We're coming up at the end of the quarter and beginning of the next quarter, and there are going to be 10 more lectures in the Computer Systems Lab series of colloquia. And you should sign up on the website, ee380.stanford.edu, and get our announcements and come and see some of the more interesting things that are going on. Anyhow, Dick, it's all yours. Thank you very much. I'm into very brief introductions now, so you'll have to explain yourself. Take care. Bye-bye.
All right. Well, thank you, Dennis, and welcome everyone. I'm sort of flat talking to screens, and with two screens in front of me, I'm particularly flat when I'm looking at the wrong screen. So my wife had this brilliant suggestion that I have pasted a picture of our son next to the camera, and I will speak to him for the next 45 minutes. So I'm going to talk about making the visible, observing complex software dynamics. I've been interested basically forever in software performance and understanding why things are slow. And it's hard to understand for very complex software why it's slow until you can actually observe what it's doing, which when it's slow is always not a match to the picture in our heads. As programmers, we think of things in very simple ways, and we tend to ignore page faults and interrupts and things that we can't quite imagine well. And it takes a long time to realize that the picture in our head doesn't match reality, and how it doesn't match reality, and therefore what's wrong and what could be sped up. So if I had my cursor in the right place, I could change slides. Here we go. So I'm going to tell you what I mean by complex software dynamics, and then go through the only 7 reasons that code can be slow when it normally runs at a pretty decent speed, the intended speed, and then now and then doing transactions or something, or database lookups, or analyzing video frames 30 times a second while a car is going down the road at 80 miles an hour. There's only 7 things that can make it go slowly now and then. So I'll go through each of those and then a summary at the end. So here's a picture of simple software. This is just a timeline running on one CPU for a few seconds. The program starts over here on the edge. It runs solid CPU bound for a few seconds, and it stops. It has a few loops that are marked here. This is what I mean by complex software. This is a couple milliseconds of the Chrome browser running on 4 CPUs. So on the y-axis, there's 4 CPUs, 0 through C, 3. On the x-axis, there's a couple milliseconds of time. And at each instant in time, at each nanosecond, the diagram shows what's executing on that CPU core. So the black lines are idle. The sine wave, we'll get back to it a little bit. The high colored boxes are operating system code, kernel code. And the half-height colored boxes are user mode code. And in this case, I've labeled all of the first instance of each user mode thread. So there's 7 different threads running here. And the arcs are showing that this system call in this thread woke up that thread and it ran here. This system call woke up that thread and it didn't run for a long time. And sometimes that's the problem you want to look at. So this includes everything, all interrupts, all system calls, all page faults, all transitions between user mode and kernel mode are what I trace. And then the post-processing turns those transitions, which is a very small amount of information, into the diagrams of everything that's going on with no nanosecond lost. So I'm focused on time-sensitive application code, so user code. I'm not interested in the operating system per se. I'm interested in when the operating system slows down, what my program is doing. My program is a user mode thing. I'm interested in code that's already been debugged. It has good design, has good algorithms. It normally runs as desired with good performance, but it has unexpected, sporadic, serious delays. Sometimes only delays that occur in a production environment, they occur in testing environments. And those are the hard things that a lot of people sort of live with, but I have spent the last 15 years or more trying to understand what's really going on, and they're then finding things that are, oh, well, that's screwed up and it takes 20 minutes to fix. So when you have repetitive code that's doing individual transactions, whatever, that only occasionally runs slowly, there's just three things that can make it run slowly. Either you're executing more code in the slow cases than in the normal cases, or you're executing the same code, but you're executing it more slowly for some reason, or you're not executing, you're waiting for something. And you'll find that in the next 15 minutes or so, will complain about observation tools that totally ignore the not executing and therefore can't tell you why you're waiting. And there's only 5 things to wait for. There's five resources: CPU, memory, disk or SSD, network, and locks, software critical sections. So the first 4 are hardware resources and the last one is software resource. In real production systems, there's nothing else that you end up waiting on. And as an industry, we generally have very poor tools for observing what's really happening, particularly in time-sensitive production code, where a tool that slows everything down by 10% is useless, cannot be used in a production data center or inside of an airplane or whatever. Inside of a database, even a 10% slowdown is generally terrible. So I'm going to talk about the system called KU trace, kernel user tracing. The book talks about it a lot, and the code, there's a reference on the slide at the end. The code is all open sourced on GitHub. It's a small set of Linux kernel patches that record every transition between user mode and kernel mode. And each of those transitions is recorded in just 4 bytes, a 20-bit timestamp and a 12-bit which transition, what happened, which event, and that's all. And I just write those in memory as fast as they occur in reserved kernel RAM. The overhead for doing that is less than 1% in a busy production data center environment. With 200,000 transitions per second per core, the overhead is less than 1%. And it's much, much less than that in simple environments. Then everything else and all of the diagrams I'm going to show you come from post-processing, the raw traces that just have these very simple, very compact transitions. So visibility, KU trace, when code is running, all the execution time of all the threads on all the cores is captured. Not just my program, but all the other surrounding programs, not just user code, but the operating system itself, because those are the sources of interference. And if you don't look at them, it's like, if you can't see them, it's like looking for the lost car keys under the lamppost because the light's good there, even though you drop them 2 blocks over. For things that are not running, you have a thread that's running and it stops running. It doesn't spontaneously stop. There's a reason. And when later it restarts, it doesn't spontaneously restart. There's a reason. So I'm going to ask questions now. I hope we have a few people. Just unmute and give your two-word answer and mute again. What are some of the reasons that running threads stop and start again? Pick one.
System call.
The what?
System calls.
System cold?
Yes, system calls.
Oh, system calls.
Or
Well,
task switching, right?
If a thread does a system call and the system call returns to that thread, it doesn't stop running. You can do a system call that then blocks, and then you go through the schedule and goes to some other thread, right?
It's end of time slot.
End of time slot, again, you end up going to get some timer interrupt and it goes
Right.
off to the scheduler and changes. Yeah. So there's a bunch of those. And if you can't see what it's doing, it's hard to figure out which things are making your threads that you want to be executing not execute. So the way I design KU trace, the reason for not executing is always in the trace. There's a thread that's running along in user mode can't spontaneously stop executing without going to the operating system. There's no user mode stop executing instruction. And because we get the transition into a particular operating system routine, we get to see why it stopped. And then later get to see why it stops. And have a little water. So if you're running along and you block inside of a sysread or something, you get that's in the trace. Later, if some thread wakes us up again, it's inside of a system call that does the wake up. I capture the wake up and then draw the arcs, and then eventually a scheduler runs and redispatches the thing that blocked, and that's in the trace. There's nothing else that can make things start or stop that's missing from the trace. So I'm going to go through now a series of 7 things. I'm going to have some more water. Of the 7 reasons that things can execute slowly or not execute at all. And each sequence, I'll show a black box of the execution times of some sample programs, and then the detailed observations of what's really going on, and then I'll talk about the root causes. So we talk about executing too much code. So here's a sample program that's doing some transactions, and there's 2 short ones, 2 more short ones, and in the middle, there's one that's 16 times longer. So this is assuming that for most transaction systems, database systems, whatever, that somebody's keeping track of when something starts and when it stops, when it starts, when it stops, but that's all we have. If we look more carefully at, in this case, executing on CPU 0, we can see that the first transaction started and stopped, started and stopped. This one somehow takes longer, and it's just all solid execution time. If we do a PC sampling profile of this sort of thing, the profile looks like this. About half the time is spent in some routine called checksum in this sample program. About 1/3 of the time is spent in memcopy, about 12% in something called decrypting checksum, and then the other couple percent are spent in a few other things, including in this profiler, samples from the operating system itself. And occasionally, in fact, with KU trace running, samples of the KU trace code itself, if it happens to be the thing that's executing just when a timer interrupt comes in. So where in that profile is the explanation of why this is 16 times longer? It's not there. It's the wrong tool. PC samples are useless for distinguishing the short transactions and the long ones. All the profiling does is it adds up lots of samples, and it smashes together all of the good cases with the bad case, reducing the signal to noise ratio of the bad cases down to almost nothing. So instead, if we take the same PC samples but record them sequentially in a trace, say this happened and then this happened and then this happened, correlated with all the other stuff that's going on, timestamp with the same time base, we get to see, in this particular sample program, this timer interrupt sample found that this code was running in a routine called decrypting checksum, and so was that one, and so was that one, and so was that one. And the sample out here was in a routine called checksum or regular checksum. And in fact, across the whole trace of the sample program, what we found is that the decrypting checksum is only run in the long transactions, and that the regular checksum and memcopy and things samples are scattered across the other transactions. So in fact, what's going on is the long transaction is executing different code, extra code, too much code in decrypting checksum, which the programmer knew was just as fast as the regular checksum, but of course it isn't. It's 16 times slower, and now we can see it. And now you know what to go fix, which your profile will never tell you. So to summarize executing too much code comes from branching. You have some if statement that doesn't normally happen, and then in the slow case, it does happen, and there's a whole bunch more code executed. Or calls that you didn't expect to happen, or callbacks. And the thing I want you to go away remembering is that profiles merge together lots of fast cases with the slow cases, hiding what's different about the slow ones, and therefore useless. Traces reveal what's different. So I'll go into executing too slowly. Are there any questions on the executing too much code?
Yes, I have a sort of comment. I mean, because you're talking about the profiler by periodic interrupts, but there are some other ways. Like for example, I'm not sure if you're aware about the Cortex-M architecture. That they have they can sample the PC every 32-bit clocks of CPU.
Yeah,
it means it's very dense. No, it is very dense. It means
very dense, but if the profile samples are simply added up and counted, they can't tell you. They don't correlate with here's where the slow action was and here's where the fast action was.
Well, actually, it is, because at every sample they send a full PC, so you know exactly where you are, and it means the similar way what you're saying. But anyway, that's just a note. So with the sort of proper hardware support, you may have a very dense sampling, which it's very dense. Every 64 clock cycles, you can have a full PC.
Sure.
You can build.
So what you're saying is they actually are recording a trace of all of the samples. They're not just counting them.
Of course, yes.
Okay, then it's a trace. Then I completely agree with you.
It's a full trace, right. Anyway, that's just because for information, I'm coming from a high-end debug and trace tools.
Sure.
That's
we did the same thing in the alpha chips in 1992 of every 64K cycles we could generate an interrupt and do a PC sample. It doesn't matter whether it's high density or low density samples. What matters is you keep them all and correlate them with what else is happening instead of just counting them.
Exactly, right. The counting only is right. Yeah.
Let me go on to executing too slowly. So here's an example of a sample program. It's a benchmark. And we run it twice, and the second time is 40% slower than the first time. And all we know is, it started here, ran there, and then get to print papers about how fast it is. But there's no information about why the second one is 40% slower. So if we trace it, this is actually a very old Whetstone benchmark. And it starts up and it runs, and it has a bunch of modules, module 2, module 3, that are tight loops, nominally measuring floating point performance from 1960s. Here's the second run. And it simply takes a whole lot longer. You can see that a few of the loops, like M2, don't take any more time. And some of the loops, like M11, get a lot longer. We can't tell yet from just this amount of information why the other ones are longer. But if something executes at the expected speed, and then the identical code executes more slowly on some other run, the only thing that can be going on is there's some kind of interference from other programs. The interference can come from shared hardware resources. There's some other program beating the cache to death, or main memory, or there's shared software critical sections. The interference comes from what else is running. So observation tools that only look at one program can never tell you what's going on if you're executing too slowly. So instead, with KU trace, we're looking at all the cores, all of the processes, all of the time. We get to see what else is going on. And in this case, it's a dummy floating point hog program that runs for 20 milliseconds or so. And 200 milliseconds, and then stops for about 200, and then runs again and stops. This is a useful technique for seeing what the program you're worried about is sensitive to. So if we look in more detail at a little bit of this, first I'm going to show you a little speedometers of instructions per cycle. So part of the tracing is at every transition, I record not only a timestamp, but the number of instructions that have been retired. And then in the next transition, I record the timestamp and number of instructions, and then I subtract and divide and get instructions per cycle. And a little speedometer pointing off to the left is showing less than an eighth of an instruction per cycle. In other words, more than 8 cycles per instruction. Diagonally up to the left is half a cycle. This is 1 cycle. It's 2 cycles. It's 4 cycles. It's a sort of a logarithmic scale. So if we look at the module 11 loop, when it's running all by itself, it's running at about 1 1/4 instructions per cycle. When this floating point hog starts up, suddenly it drops by a factor of 3 and is now running at about 3/8 of an instruction per cycle. And then when the hog stops, it picks up again. And these are a few microsecond time scale time ranges. And the module 9 loop over here, when it's running at full speed with no interference, it's running at about 3.5 instructions per cycle. And when there's interference, it drops down to about 2.5, so it's about 40% slower. So from the trace with the instructions per cycle over all of the little bitty pieces, you can see exactly that module 2 doesn't slow down. The reason is it doesn't do any floating point instructions. It's a bogus benchmark. And you can see that module 11 does lots of floating point divides and slows down more than the other ones. So you get to see exactly the interference. And of course, if you have interference, you either need to fix your program so it's less sensitive to the interference, or you need to fix the other program so it doesn't interfere as much, or you need to run them separately. But once you know what the interference mechanism is, you can decide what to do about it. And usually that decision is pretty simple. So executing too slowly, in summary, comes from other threads, other programs, the operating system itself interfering with our program. Or it can also come, I haven't talked about it here, from running on a CPU where the clock frequency has been reduced dramatically to save power. This leads to programs that run more slowly on nearly idle machines than running on really busy machines, because they're running 5 times too slowly at like 800 megahertz instead of 3.9 gigahertz. Can also run slowly due to slow exits from power saving, that chips go into power saving and reduce the clocks and reduce the voltage levels and reduce the clocks and reduce the voltage levels. Coming out of that, like Intel Deep C6 sleep state, can take 30 microseconds. And if you have program dynamics, perhaps bouncing back and forth between threads, you can keep paying that 30 microseconds many times in a row, very close together, and it's a real slowdown. So go away with the idea that microsecond scale instructions per cycle reveals the interference between tasks. Looking at instructions per cycle over 2 seconds tells you nothing. Looking at it over a millisecond or so doesn't tell you very much, but looking at it over just these microsecond scale execution intervals at every interval tells you a lot. So waiting for something.
I actually had a question.
Yeah.
So could you go to the previous slide, please? So here, I agree that you could find the interference between tasks, but in the example you showed, you mentioned that it was the floating divide unit.
Yeah.
So does the trackers help in identifying that as well? Or do you have to manually look at the 2 programs and infer that, hey, maybe it's this unit?
Well, first, these are 2 CPU cores that are hyper-threaded. That's why there's interference between them. If this program were running on a different core in this machine, different
Sure.
physical core, there wouldn't have been any interference. I just happen to know that the interference is from floating point divides. But usually if you're interested in performance slowdowns, it may not matter what the actual interference mechanism is. It's just that, when that runs, this goes slowly. And so what are we going to do about it? Sometimes it does matter, but there's only 3 high-level choices. The interference is at memory, or it's at shared functional units that aren't fully pipelined, hence floating point divide, or I've forgotten the third one at the moment. Anyway, it's this, it's a branch misprediction. If something is causing branch misprediction, you can slow down a lot.
Yeah, thank you.
Does that answer your question?
Yeah, it does. Yeah.
Okay, good.
Or cache
So I'll
swiping,
go on.
right? Like kind of if the cache is like being constantly, swiped away, that's also could happen. You have to recache data, right? Again and
Yes.
again.
For instance, when you go off to the operating system on a page fault and it does a copy on write, it copies 4K from a read-only page to a newly allocated read-write page. That 4K copy can fill up 4K of your cache and display stuff. And then when you come back, what you see is you run more slowly right after a page fault. And that's a direct form of interference from the operating system, not from other programs. And we see those in traces. I'm not sure if I have an example. I do have an example of one. Actually, I can show you that now. Okay, so unfortunately, I don't get any feedback of what you all see. So I'll start over quickly. And this is Hello World running on 4 CPUs. And I started it over SSH. So the SSH daemon here is getting an interrupt, a network interrupt. This is the software interrupt handler, bottom half for RX. It wakes up this other thread, kworker, which wakes up bash, the operating system shell, which does a clone call, which makes a copy of itself bash with a different process number, which does an execvc, which brings in hello world and starts to execute it. These are markers I put in at the very first line of hello world or the very last line. And we can see that hello world itself runs for 154 microseconds. And if you zoom way in, I include at the edges what the approximate overhead is of KU trace itself. So you can tell if you have a whole lot of really, really close together things, whether the overhead is too much. If we turn on the instructions per cycle on all these little pieces, what you can see sometimes, this is probably a bad example, but you can see if the user code is running quickly and then you page fault, page fault, page fault. Well, actually, you can see here, the page fault code here runs slowly, a little faster, a little faster, a little faster, a little faster. This is the page fault code, bam, 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 putting its own stuff into the cache. And then when that sequence finishes, if the user code had a lot of stuff in the cache that got displaced by these page faults, the user code would run slowly out here. In this particular case, the user code was running slowly. Well, there it was running faster. And then after the page faults, it's running slower. So that's the kind of interference you can see from across the operating system. Okay, so we're off, waiting for something. So when you're waiting for something, it means it's not executing. So profiles that sample PCs aren't going to tell you anything. And instead, you get to see what it is you're waiting for. So here's an example of waiting for the CPU. We have 3 threads in this other sample program running over here. The 4th thread gets a software lock and these 3 block. The 4th thread frees up the software lock. 2 of the 3 start, and the 3rd one doesn't start for a long time. In fact, this is 2 milliseconds later. The question is, why is that guy waiting? And of course, from the timestamps or profiles or whatever, you can't tell. If we look at the KU trace, this is now sorted by process ID instead of by CPU number. Here's the 3 processes running. Here's the 4th one. there's a pink line here that shows that it's holding a lock, and the color of the line says which lock. And in the HTML, shift clicking on the line tells you by name which lock. And then at the end, this frees the lock and wakes up the other threads, except one wake up takes a long time. I'm going to look at what's really going on there. At this point, the fourth thread first does a write. It's a debugging write, and that write wakes up a process called gmain, which is the GNOME display process, which in turn is going to wake up the SSH process, not shown here, because I was running this login. And so after that write, the thread that was holding the lock sees that when it frees the lock, that there were other waiters, and it does a few text system call here and wakes up the other three waiters. At that moment, there are 5 threads and only 4 CPUs. There's the 3 threads that are getting woken up. There's the gmain thread, which wasn't in the picture in my head. And there's the thread doing the write that's about to finish, but is not yet finished. And then there's a scheduler screw up that when this CPU gets free a little bit off to the right here, the Linux scheduler doesn't run the waiting thread. It doesn't run it until there's a timer interrupt way out here. And it looks around and says, oh, there's something I can run. And meanwhile, in here, there's a couple milliseconds of 2 CPUs doing nothing while my third thread waits. So there's really a Heisenbug here. If you take out the debugging write, there's no 5th thread, problem goes away. If the debugging write goes to a local disk instead of over the network via SSH or whatever, there's no 5th thread, and there's no screw up. If the scheduler didn't have the screw up, you could have the write and the extra thread, and there would be a very tiny performance bug that you wouldn't care about. So it's this combination of a debug write and SSH access and the scheduler screw up that gives you a bug. And so the good news is that KU trace has such low overhead that it doesn't disturb Heisenbugs. They're still there and you can see what they're doing. So to summarize, waiting for CPUs, you can wait for CPUs because they're all busy. You can wait because the scheduler has too strong affinity for where a task last ran, and it won't move it to another core soon enough. The time constant here, because you're trying to go back to warm cache, is only about 50 microseconds, while the Linux scheduler default for giving up and moving a task to a different core is 12 milliseconds. There's also delays from coming out of power saving states and the complex interactions. Let's see. So go away the idea that wake up events tell us what a thread was waiting for. In this case, due to the scheduler screw up, it was waiting for time to have passed. It's the timer interrupt that wakes it up. So waiting for memory is another little sample program. This one is a parent task that uses pthreads and clones the child task. Except the child task takes a long time to start, and we don't know why. And if you look at what's going on, this is the parent task. It's actually doing a clone call here. It's doing another one. It's cloning 4 children. The first one turns out to be the one we're looking at. And then it's cloned its 4 children and it stops running. This child that we're looking at starts running here, immediately takes a page fault because the parent, in cloning a child, makes a copy of its page tables, marking all the pages, all the shared pages read-only, and then depends on copy on write to make new copies of the pages that the children actually touch. So in detail, here we have at step 1, this clone makes a read-only copy of the parent page tables. At step 2, the first child takes its first page fault, trying to access one of those, but it can't access them because the parent hasn't actually finished initializing the shared page tables. So this guy blocks waiting for memory access. Eventually, the parent runs again and finishes the page tables and wakes this guy up, and then it's just waiting for the scheduler, waiting for a CPU. The reason that the parent blocked and didn't finish the page tables back here is that after it spawned 3 children, there were only 4 CPUs and there were 5 threads running. It turned out that the scheduler had the parent thread stop and only restarted it when the children stopped waiting to get access to the page tables. So this guy finally finishes the page tables, this guy finally runs, and then it does a whole bunch of initialization writes and takes 60 page faults in a row, doing all those copy on writes. And only then out at the end does it start running the real part of the child task. Maybe the few hundred microseconds here doesn't matter, but now at least we understand what's going on and we can decide whether to do something about it or not. For instance, by allocating a bunch of memory for the children ahead of time, that they, if you go between parent and child lots of times, that the children can use pre-initialized memory. So it's a summary about waiting for memory. Waiting for memory can come from all the memories allocated. It can come from trying to do a large contiguous allocation in a badly fragmented memory. It can come from just paging to death, or it can come from other threads that are manipulating page tables and temporarily locking them out, except that the temporary is much longer than you might have thought in your head. So that's for memory. For disk, it's a little couple of sample programs. The first one reads a 40 megabyte file, takes 680 milliseconds. Second program reads the same file, takes 1,330 milliseconds, almost twice as long. The question, of course, is why the slow one? And if we look at a trace of these two, this first program opens the file, does a single 40 megabyte read, and then blocks waiting for that to finish. And during this whole 680 milliseconds is using no CPU time. And then at the end, it gets an interrupt saying, oh, the read's done. And then it finishes doing what it's doing with that and closes the file. The second program opens the file and does 10,240 4K reads. The first read takes a while. And then this program keeps getting, oh, this read finished. It gets the interrupt. It starts the next read. That blocks. That read finished, et cetera. And it uses up a huge amount of CPU time and twice as long. And if we look at detail of those reads, what we see on a different CPU core is the interrupt handler for the disk, the hard interrupt handler, the soft interrupt handler. Soft interrupt handler wakes up our read. Our read happens in this little bit of user code. It does a read for the next 4K, and that blocks. That's the scheduler switching to the idle task. And then when we get the interrupt from the disk and wake this guy up again, this little bit here is finishing the read that started back here. And then the user code goes around the loop and starts another read that doesn't finish until way out here. And this repetition rate's about 150 microseconds. The blocks coming off this particular slow disk are coming every 66 microseconds. So we're missing every other revolution, even in the presence of disk hardware and microcode that's reading ahead and buffering up things. And there's just a lot of turnaround time between the CPU saying go read and getting all the way out to the disk where the disk says, oh, I have a block. It's in my on drive DRAM buffer WAMP here, but that still takes many microseconds to go through that path. So if we are waiting for disks, it's a fairly short summary. The disks are all busy, or you're doing inappropriate small transfers, or for instance, you're going off to a disk that has a write buffer and it's in the middle, the microcode inside the disk is in the middle of emptying that write buffer. And what it's buffered up are writes to a bunch of different places on the disk, and emptying the write buffer involves 12 seeks at about 10 milliseconds each. And suddenly you've lost 120 milliseconds before the microcode will look at your read. This happens all the time. The effect that our data center people told us when I worked at Google is when you're doing writes, everything gets slower. It's not true that the writes themselves are slower. It's true that you get this interference. Or for SSDs, for flash memories, when you're erasing flash blocks, the erasure cycle takes about 10 milliseconds. And if the microcode or the hardware and the controller for the SSD is off erasing flash blocks, nobody else can do anything. You can't read or you can't write. So those are the kinds of things that it's hard to see, but you can at least see that you're waiting and get some clue of why you're waiting. And then there's the usual complex interactions. Seeing the interrupt activity is what tells you what you're waiting on and how long you were waiting on it in detail. So I'll do network. Here we have 12 network remote procedure calls. So this is sitting on the client doing the call. So client does a call, and sometime later, the response comes back from the server somewhere else. Client does another call, the response comes back, does a call, response comes back about 3 times late. It takes about 3 times longer before the response comes back. And these are nominally all the same sort of transactions and should all be about the same speed. So we want to know why those are slow. This is a little messy slide, but we'll go through it. The client program is running on CPU 0. And what I want to highlight is here's a write of the beginning of that transaction. Here's the write that's sending away over the network the request for that transaction. Here's the write that's going over the network for that one. And there's writes for each of them, and they line up in time near the beginning of each transaction. There's a little code that executes before you get to the write. If we look at these 3 writes in detail, 1 fast one and 2 slow ones, we can see what's really going on. Here's the fast one. Here's the write on CPU 0. Here's the packets crossing the wire 20 microseconds later. There's actually 3 packets here. It's a 4K write, it turns out. And in KU trace, I timestamp right at the NIC. Here's where the packets are given to the network hardware. And for packets coming in, again, at the NIC inside of the TCP or UDP code or whatever, I timestamp, here's where the packet came in. The second write, the write is here, but the packets aren't hitting the wire until 600 microseconds later. And the third one, they don't hit the wire until 300 microseconds later. What's going on is over here on CPU 1, there's a totally different program running, and it just started at this point, a megabyte write over the network. Packet, 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 packet. And the things that's delaying these guys is my 4K worth of packets are getting queued up behind packets going out from the megabyte write. And when the megabyte write finishes, things go back to normal. So that's the level of detail that lets you see which hardware resource might be overloaded and why you might be waiting. And it turns out network delays, there's lots of sources of network delays. And the thing you fix is different for each source. It could be when you send, in this case, a packet, that there's delays in the outbound kernel code. The TCP code is off doing something else or has some unusual path that you weren't expecting that takes a long time. Or the network itself can be busy on the outbound side. Or there can be in the hardware network, hardware path, with lots of switching racks between lots of machines and something like a data center that can be slow. When you get to the other end, the machine receiving the packet, it turns out most network cards hold off interrupts saying, I have stuff. They may DMA the data into a kernel buffer, but hold off interrupts in order not to generate so many interrupts per second that it overloads the CPU just doing interrupt handling. So it might be 20 microseconds before the interrupt is actually delivered saying this packet's arrived. And again, on the receiving end, the kernel code may be delayed. The TCP code may be off doing other things or whatever. It's also possible on the receiving end that the user code that you're sending this information to is actually hasn't gotten to the point where it's doing its read or receive message or whatever to get the data, that is off doing something else, and it simply hasn't asked for the data, which boom, went all the way across. And in each of these cases, the thing you fix is on this machine or on that machine in the user code and the kernel code and the hardware. It's important. And seeing where the packets actually go across the wire is enough to help you distinguish which case it is and therefore what to go fix. So that's my summary on waiting for networks. And we have waiting for locks. This is the fifth of the waiting things.
One question. So do you have
sure.
any possibility to see like two machines like in the same time
yes.
lane?
Yes.
Okay.
Yes.
Right. Okay.
You run KU trace on two machines. The timestamps are all mapped in post-processing to the get time of day, the user visible wall clock time.
Right, something common, right?
So you get time of day on machine A, you get time of day on machine B. You have packets going between them. You can then correlate where the delays are. Now, the get time of day on the two machines won't be the same. They may differ by 20 milliseconds. They may differ by 120 milliseconds. They will differ from hour to hour. Some people build really expensive, fancy hardware, and they use measured wire lengths from GPS receivers and stuff to try to reach the point where all the machines in a room have the same get time of day. And I find that's just sort of a waste of effort and money, because if you send a packet here and it arrives at some other machine a while later, if you can identify which packet it is on both ends, you can, for the things that aren't delayed, and there should be a lot of things that aren't delayed, and only a few things that have interference of some form. For the things that aren't delayed, you can actually line up in time what the get time of day offset has to be between those machines and come within a microsecond or so. And that's good enough to understand all of the correlations.
Right, you can calibrate, right, kind of on this.
Yeah, and so when I teach courses from this material, which I've done 4 times now over the last 4 years, one of the exercises in the third week is the students write the program that correlates the time on the two machines, so they know that you can do it in software and that it's trivial. And I hope that those students then don't end up in companies that think they have to go buy expensive hardware. So does that answer your question?
Yes, it does, yes.
Okay, good. So I'll go on to waiting for locks.
I'm not coming from very expensive hardware, so.
Yeah. So here's 3 threads. 2 of them, the top one and the bottom one, are waiting a long time for a lock. This is only, 20 microseconds or so, but they're waiting a long time, milliseconds. We'll get back to that in a second. And this middle one has the lock, uses it, has a lock, uses it, has a lock, uses it, doesn't have it here. The question is, what's going on and why are these guys never getting the lock? So here's the KU trace of what's going on. The dotted lines up here are this thread is waiting to get the lock, and it keeps waiting, even though it's not running, it's running, it's not running, it's running, it's not getting the lock. The same thing at the bottom. And this middle thread has the lock, solid pink line. And when it frees the lock, part of the mechanism for freeing the lock says, oh, there are threads waiting to get the lock. Go to the operating system futex call, and it does the wake ups of the other threads. Unfortunately, what's going on in this particular trace is this guy does the wake ups before these other threads wake up. Our middle guy, bam, goes and gets the lock again. Bam, goes and gets the lock again. This goes on for 84 milliseconds. So this thread has captured the lock and is starving out all the other threads. And the flaw is when you free up a lock, you have to not go get it again and wait long enough for the other threads to get a chance. So how come the other threads don't start up sooner and jump right in? Because here's the wake up, and it's a good couple microseconds, microsecond and a half later before on this other CPU, this thread actually starts running. It's waiting for a CPU in here. And that's just the hardware delay of the cross-core interprocessor interrupt saying, go run the scheduler here, there might be work for you. And so if you wake stuff up and you don't wait some small number of microseconds, these guys can get starved out for a long time. And then eventually by fluke, somewhere in here, there's a like a timer interrupt that slows this guy down just long enough that these others get a chance to get in before. And then one of the other threads will get the lock and then hold it and starve out everybody else for a while. So for locks, if you're waiting on locks a lot, it's of course the other threads that are holding the lock that need to get fixed, not your program that's running slowly. And in order to deal with that, you have to know first that there are other threads holding the lock, and that's what the problem is. And second, you have to go figure out which threads those are and go fix them. When I was working at Google 5 years ago, I did a search over all the source pool. You know, it's a search company, a whole source pool is searchable. I searched for declarations of software locks, and there were 135,000 of them. And we spent months sometimes. We didn't have at the time a good way of figuring out which lock it was, because the locks were actually, dealt with through libraries, and the libraries reused the same memory addresses for data structures for the locking mechanism, so that you could, at the time you went to get a lock and couldn't get it, you could get the address of what the lock data structure was, but it was always the same address, or the same, always one of 20, independent of what the real lock was. So tracking back to the line number of the declaration of the lock that was the problem took us forever. But so this is another example of when you're running slowly, the thing to fix is not the thing that's running slowly, it's somewhere else. So it's important to design in being able to see lock acquire and hold and release, and to be able to figure out which lock. So that's the 7 things that can make stuff run slowly. Executing too much code, executing the same code but more slowly, or not executing, waiting for one of the 5 shared resources. Being able to see what every CPU core is doing every nanosecond is what makes the invisible visible. And as an industry, we have very poor tools for doing that. So I'm hoping that some of the students who look at this think about after they finish their theses, in their work lives, to go out and implement things like this, so you really can see what's going on. It pays for itself really quickly. I made the occasional changes after being able to see what was happening at Google that saved 10 years of my salary.
Hi, Dick. Can you hear me?
Sure.
Yeah. Can you give some clues about how KU Trace is able to do all this magic? I mean, it seems to need no CPU thread. It seems to need no cache, and somehow it's able to give you all this output, but without changing, branch predictions and stuff.
Yeah. Well, the patches in the Linux kernel take about 40 CPU cycles to record one entry. Because the entry is just 20 bits of timestamp reading the RDTSC clock in Intel chips, or the system time clock in ARM chips. I've got this running on a Raspberry Pi 4 also. And there's 12 bits of which event, and that's all that's written. And those 4-byte aligned values are written into per CPU core memory blocks. So there's no thrashing of the cache between recording on different CPUs. And then periodically a block gets filled up, and there's a little time spent allocating the next block that involves an actual lock between the KU trace on different cores. And then everything else is done in post-processing, turning the raw traces into events with time of day timestamps, turning those into time spans instead of edges, turning the time spans into a JSON text file, turning that into HTML.
Yeah, right.
But in detail, you should go read chapters 15 and 16 that explain how this is done.
So the basic, how much code is there? I mean, it doesn't seem to have any branches. It just knows which 32 bits to send.
Yeah, there's one branch in the code that says is tracing turned on, and almost all the time tracing is not turned on, and so that branch is perfectly well predicted. And then when tracing is turned on after the first time on each core, then it's perfectly well predicted that tracing's on. There's a few other tests incrementing the pointer in each CPU block of where the next thing goes. I test whether it's reached its limit yet for that block. So there's a test there, but there's 8,000 entries per block. So that test is also well predicted. No, we're not at the end, we're not at the end, we're not at the end. And then one time out of 8,000, we are at the end. And there's one other test in the allocating new blocks to say, have we filled up the trace buffer? And the user did not ask it to wrap around, flight recorder mode, but asked to stop when it fills. We test that we're at the end and say, okay, stop. That's it.
You're sharing a buffer with your output. You're sharing some kind of a buffer, hardware buffer.
No, just pre-allocated kernel memory. I'm just writing into regular memory.
Writing into memory. Okay, thanks, Lon.
That's the only thing that's fast enough to record this stuff. I'm literally getting, on average, a new event, a new transition between user and kernel mode every 5 microseconds.
Yeah, this was my question. What's the bandwidth of the data, sort of in, say, bits per second or megabits? That's my question, kind of. What is the total bandwidth out of the core, or say, per system? What is it?
Sure, it's 200,000 events per second was the maximum we saw at Google in production live data centers during the busiest hour of the day.
So about 1 megabyte per second?
So if I could finish. So at 200,000 events per second at 4 bytes each, that's 800K per CPU core per second. If you have 20 cores, that's 16 megabytes per second.
Mm-hmm. Okay.
If you have 20 cores and you're in a large data center kind of environment, you have a few hundred gigabytes of RAM. And so 1% of that RAM, you've got enough room to record for a minute or two at full rate across all the cores. If you have a Raspberry Pi controlling a thermostat or something, still with 1% of the CPU and 1% of the RAM, you can record meaningful traces.
Okay. Yeah, that's
the key is that each event is only 4 bytes. Right. The competing things like ftrace, each event is 48 bytes. And the bandwidth is too high, and the amount of RAM it takes is too high, and the amount of time you can afford to record contiguously is too low.
That's a problem.
So we have a few references. There's the book, there's the matching code at the Addison Wesley website, which due to mediocre branding is called Informit IT. But the code is now also on GitHub under DigSite's KU trace. If there are any students who are looking at this who have access to the spec benchmarks, I would love to get together and trace the spec benchmarks. The spec 2017 or whatever is current, and see which ones are measuring what they claim to be measuring and which ones aren't.
Mm-hmm.
And that's it. So any other questions?
12 bits seems like magic.
No, you don't understand. This is just an engineering talk. This is very carefully engineered. I counted cycles for every bit of the code that records one entry. And I did the back of the envelope bandwidth calculation up front and the overhead. And my budget at an event every 5 microseconds, my budget for being no more than 1% overhead is 50 nanoseconds to record an entry. That's shorter than a cache miss timeout to main memory. So that says just by first principles, an entry has to take less than a cache line. In fact, it has to take a lot less than a cache line. So the only reasonable choices were 4 bytes per entry or 8 bytes per entry. Nothing else would be fast enough. So I chose 4. I actually ended up packing pairs of call return into an 8-byte entry because one of my cohorts at Google long ago, Ross Barreau, who wrote a bunch of the initial Linux TCP stack, he said, you know, it would be really helpful when there's a system call to get a little bit of information about what the arguments or return value are. So by packing a contiguous call return pair into one 8-byte entry, that freed up enough room not to have 2 complete timestamps, but 1 complete timestamp and then just a delta time in a byte. And that freed up 2 bytes where I could record the low bits of the first argument to a system call, which were often useful, like which IO device is being read or written. And another byte was left for the return value from a system call. In particular, it was just big enough to hold all of the standard Linux error codes, including the one that says there was no error. And if things don't fit because the delta time is too big or the return value is too big, then we take a separate 8-byte entry for the call, wasting half of it, and an 8-byte entry for the return, wasting half of it. But that only happens about 6% of the time. The other 94%, they pair up. And in fact, when I started pairing them up, it got faster because I didn't have to allocate another entry. I just overwrote the unused bytes in one entry. I was surprised that it got a little bit faster.
So if you're using the system on a quote modern machine, which has speculative execution at multiple levels and multiple speculative threads, does it make things much more complicated?
No. You know, so thread does a system call. You're going to spend a lot of time in the operating system software and hardware doing that switch from user mode to kernel mode and saving registers and getting ready to the point where somewhere inside the operating system you can finally do a call to a C routine instead of to assembly language. I just patch in at that point, do my 40 cycles worth of stuff and get out.
Okay.
The operating system calls are very costly, so stuffing 40 cycles is not that much, right?
But in particular, because I go off and separately measure what my overhead really is, and I put in the little diagonal white lines, you can see where when you zoom way in on any of these, you can see where my overhead is starting to be the same order of magnitude as the real code time span. And if it's not the same order of magnitude, then you don't care.
Do you have,
but yeah, it took careful engineering.
do you have simulation tools that you can run all this stuff, but on a simulator instead of on real hardware?
No.
Sorry.
Simulators are way too predictable, right? So you need chaos from the hardware.
I assume that people have like x86 or ARM simulators that include simulating all of the kernel code instructions, and that if you had an ARM Linux kernel and you ran it on a simulator that included my patches, it would run.
Yeah, but from simulator you will never have that sort of real life disturbance as which you need and you want to see. The simulators are usually not simulating bus contentions or whatever it is, right? I mean, they run the code, and there are some of them, but they are very slow. So
I mean, what I'm looking at is interference between multiple CPU cores interacting, touching the same data and stuff. And I don't know of simulators that do that really well, as you say.
Yeah, no, I know a simulator is slow, but when I'm doing research, I have time to look at stuff if something is really confusing me. But I get, I've got my my hypothetical MX computer, which doesn't exist in real hardware, but I can simulate it. I'm sitting here trying to imagine watching KU trace on my simulator.
Yeah, so does MX have an operating system, have kernel code and user code?
There's something called NNIX that I never wrote, but somebody in Japan has done that. But they're basically kernel mode. I mean, there's the machine has one bit where you're in the kernel or not, and you have access, to lots more memory and so on.
Yeah. So I think I would enjoy someone porting the patches to do that. I think it would be straightforward.
Yeah.
I've been looking at porting the patches to a RISC-V machine, but unfortunately, I found that there's no decent time base.
Yeah.
Really?
The board they gave me has a microsecond time counter, which isn't good when you're in a microsecond. You do 1,200 instructions.
How hard?
And it takes 400 cycles to read it.
Are you able to port it to an alpha chip?
I could. There's no commercial value in doing that. I'm really interested in helping people fix real performance problems in real code that they're running today in time-constrained environments.
Like all the cores, RISC-V has the cycle counter, which is very, assuming the CPU runs the same clock. So that's
it's useless.
Useless.
Yeah, I mean, I have one of these. I've been using it.
Okay.
The cycle counter stops when a particular CPU is idle. And so even if you started out with all the cycle counters synchronized across all the 4 CPUs, which you can't start out with, but if you could, they would immediately get desynchronized. And if you have different timestamps on different CPU cores, there's no way to line up, this guy woke up that guy, because there's no common time base.
I see. I wasn't aware. I knew the counter exists, but I never look at that such a granularity. Usually these counters have option to run either always or stop sometimes. But if it doesn't, that's.
My experience has been that there's lots of chip designers who speculatively put in, oh, this would be a wonderful feature to have and people could use it to see what's going on. But nobody actually uses it. And when I go to use it, what I find out is they're useless. They've spent a bunch of hardware on something that's no good.
That's the problem.
Sad to say. I have a SIGARC blog, a couple of articles in the January SIGARC blog about the 4 performance counters I'd like to see, all to be read in one cycle on each CPU. That's all you need. That's all I need here. In fact, one of the problems with KU trace for x86s is to do the instructions per cycle, I have to read the number of instructions retired. In order to read that, I have to, at the beginning of a trace, go set up a bunch of global state to tell the hardware which thing to count in counter number, whatever, where we've got a dozen generic counters. Okay, and having to do that setup on each core, because you have to change global state in order to find out how many instructions are retired, it means that nobody else using the machine can use those counters because I just took one away. And it means in particular, the operating system can't use any of those counters. And so what I'd like to see is an instruction that says, read the cycle counter with the guarantee that the cycle counters are all the same across all the cores. In other words, the thing you're reading is a mirror of something that was set at boot time, and that the read only takes 1 cycle. I mean, this whole idea of reading the time and waiting 400 cycles to get it means that you can't read it more than about once every 40 microseconds without huge overhead. And you don't know when 40 microseconds have elapsed if you can't read the time.
That's a catch-22, I believe.
Yeah. Yeah, so I gave up on that and sticking with x86 and ARM.
So Dick, I don't know, can you see I'm holding up a book?
Yeah.
Okay, so I gave a keynote talk at IFIP Congress in 1989. That was, 30 some years ago. And I decided that I would, since Hilbert had given a famous address once at an international congress of mathematicians saying what problems should people work on, I gave a challenge problem, and my challenge problem was to investigate 1 second of computer time.
Yes.
And here's what I said. Make a thorough analysis of everything your computer does during 1 second. The computer will execute several 100,000 instructions. I'd like you to study them all. The time when you conduct this experiment should be chosen randomly. You might program the computer itself to use a number generator to decide what second should be captured, and so on. But then there were issues about you don't have access to the source code and so on. But anyway, I just wanted to say that I consider that probably you have solved this challenge problem at last.
Yes, I have. Thank you. Is there a $2 check?
$2.56.
And now computers runs millions times faster than you wrote it.
Maybe we should stop on that note.
I was going to say, I think we've reached the point where inflation is going to cause problems. In any case, thanks, Dick, very much. It was a great talk. I think it's an important piece of work, and one which we're going to be appreciating more and more as the decade proceeds. So thank you very much for the work you've done and for participating. And thank everybody for listening.
Right. And thank you for the invitation. You all take care.